Okay, so we're going to talk about a much quicker way to do derivatives. And we're going to start with the formal definition of derivatives, which we covered in the previous videos. So in the upper left-hand corner, of course, there it is, the limit as h approaches 0 of f of x plus h minus f of x over h. And what I've done here on the right is I've shown you three different applications of this formal definition. The first one is for x squared, right over here. And then the second one is for x cubed. And then the third one is for x, okay? And hopefully you've done at least the x squared one. We may not have done of x cubed in the class, but that's a pretty easy one. It's just a cubic expanded and a linear, which we've done many times. And over here on the right side, I put Pascal's triangle, right? And that's really important for Pascal's triangle because when we do these expansions, right? So over here, when we do f of x equals x squared or f of x equals x to the cube, there's a quick way to do it using Pascal's triangle. And if you remember, this is, let's say, for example, x plus 1 squared, a typical, I'm sorry, x plus 1 to the 0 power. And this would be x plus 1 to the first power. And this would be x plus 1 squared. And this would be x plus 1 cubed. And this would be x plus 1, sorry, that's a 1, to the fourth, etc. So hopefully you did this in pre-calculus. And you'll recognize that these numbers here represent the coefficients, right? So obviously x plus 1 to the 0 power is 1, so it's 1, that's it. X plus 1 to the first power is 1x plus 1. X plus 1 squared is 1x squared plus 2x plus 1. X plus 1 cubed is 1x cubed plus 3x squared plus 3x plus 1, etc. All right? And the reason why that's so important is you can see it right here, right? So for a squared, now it's not x plus 1 in this case, it's x plus h, right? But for x plus h squared, right, it's 1x squared plus 2xh plus 1h squared, right? There's the, right over here, right? That's the 1, 2, 1, okay? And down here in the cubic, so let's look at the expansion for x plus h cubed, right? 1, 3, 3, 1. Look at the triangle, and it's going to be 1, 3, 3, 1. And of course, for fourth power, it's going to be 1, 4, 6, 4, 1. Fifth power, 1, 5. 1, 5, 10, 10, 5, 1. So remember that as we go through these three derivatives, and we can kind of see there's a pattern, right? So that all of this discussion is about a pattern in using this definition of the derivatives and its limit as h approaches 0 and seeing if we can find a shorter way to do it. And in fact, that's what happens. So let's take a look. Let's take a look here. I want you to notice that every highest power of the expansion, so in the case of x plus h squared, this term and the minus f of x always go away, right? Let's look at the cubic one, x plus h cubed. So the highest power term here and the minus f of x, that's coming from, right, from this part of the formula here. Minus f of x, right? That's what this is, right? Minus f of x. So whenever we take a derivative of x squared or x to the third, we're never going to see an x squared or an x to the third in the answer because that highest power term is going to be subtracted. What we do see, right, the first thing that we see is this 2xh, see, 2xh. And here, 3x squared h, all right? Now the thing is, of course, and you've done these before, so this shouldn't come as any great surprise, is after those two terms are gone, everything else has an h in it, and the h's are going to reduce with our denominator h, right? So here, on the first one here, f of x, on this first one, f of x equals x squared, we get, see, 2xh plus h squared. So this h, that h, and this h reduce, right? And they're all ones. And what you get at this top one here is just a 2x. I didn't want yellow. Is a 2x. Because, of course, the h's reduce, and as h goes to 0, right there, we get 0 for this h term, right? H to the first becomes 0. Let's look at the cubic expansion, right? So for the cubic expansion, this is the first term that appears, right? So back up here, that was the first term. This is the first term that appears, so it's 3x squared h, right? But as happened before, the h's cancel out, right? So this h and this h, this h, this h becomes 2, this becomes 1. Reduce, right, to 1. I don't like the word cancel out, so it reduces. I'm going to change it. Again, notice the x cubed. These x cubed terms are gone. They subtract from each other, so they're gone. You never get the highest power. You always get the next term. You always get the next term. And same thing down here. The only thing about down here on this third one is x minus x is 0, and the h is reduced. So it's a kind of a unique case here, and you get 1. And the limit as h approaches 0 of 1 is 1. Right? It doesn't matter because it's not dependent upon h. So if you look at these three derivatives here, right, they all come from Pascal's triangle, right? Or they come from the expansion. So in the case of squared, see, in the case of x squared, in the case of the squared term, right, this is the number. It's the number 2 that goes in front. So right over here, right? This is the number 2. You see the three number 2s? Okay. In the case of the cubic expansion, this number 3, right? So in other words, when you try to take the derivative of x to the third, you get a 3 here because that's from this term, the second term, right? If you were to do the derivative of x to the fourth, you would get a 4x to the third, right? That would be the first term, 4x to the third. So you see, this row in Pascal's triangle, and it goes down forever, is always equal to the power, right? It's always equal to the power that you try to do the expansion on because it's the second term. So 2, 3, 4, 2, 3, 4. All right? So what does that lead us to? Well, that leads us to when you take the derivative of x squared, right? And there's two ways to write that. I'm going to actually write both. So if I take the derivative with respect to x of our function y equals x squared, okay, I'm going to take the derivative with respect to x of both sides. We're going to talk a lot more about this in future videos. Of x squared, okay, we get dy dx, which we often write as y prime, by the way, so I will write that y prime. These mean the same thing. The derivative is, remember, 2x. So what do we do? Well, this is called the power rule. We take this power of 2 and we move it down to the front of the coefficient of the answer. So it's 2. And that's from Pascal's triangle, right? It's the second term in the expansion because the x squared term disappears when you do minus f of x. So it's 2x, and then of course, remember, we're always 1 power lower when we write that term, right? We're always 1 power lower. I'll do it again here real quick. So x plus 1, or actually x plus h, we'll say, squared, right? We get x squared. That term's going to go away, right? We're going to lose that term. And then the next term is, of course, plus 2xh, right? There it is, plus h squared. Now, when you set h equal to 0, this term goes away. But remember, this h reduces. It doesn't go to 0. It reduces in the previous, right? Because we're dividing it all by, if you don't do the whole thing, you do a minus over here. You do the minus f of x. And then you don't divide it all by h, right? Which I'm not going to leave there because that would be incorrect. But that's the idea. And so you can see the pattern. This is the first power because it's the first power right here. See, it's the second term. All right? So that's how the power rule works. You take this number, you multiply it by the coefficient. So if there was a coefficient there, we'll do that in a second. X to the first, you drop the power. Pretty easy, right? Much easier than the formal definition. All right, so let's do another one. We'll do y equals x to the third. And we want to find y prime, right? dy dx. So I take this number at the top. So I take the coefficient here. I mean the exponent, excuse me. I take the exponent. And I move it to the front. And I get 3x, and then I drop this by 1. So 3x squared, right? And you can see in the book, we have a, a formal little formula for this, but it's really just put this coefficient here, drop the power by 1. Of course, as we talked about, and we've had lots of discussions about this, if it's a linear function, you don't really have to do any work because that's y equals mx plus b, right? Y equals mx plus b. So in this case, right, it works. Y equals, now this is x to the first. So I take the 1, I move it to the front, and I multiply it times, right? So that's 1. I guess I'll leave it in yellow. No, let me use blue. 1 times 4x, but don't forget I've got to drop this power by 1, right? So this power has to subtract 1, so it's 4x to the 0, which is 1 times 4 times 1, which is just 4. And that should come as no surprise, right? Because you already know the slope in a linear function. It's always the m, right? It's the m. And so we got the answer. But my point here is we used the power rule of derivatives. We took the 1, multiplied it in front, dropped it by 1 power, and this is exactly what you get. And then the derivative of a constant. Oh, and by the way, this is y prime. My apologies for that. So what about the derivative of a constant, right? So let's say we had a horizontal line. Well, what's the slope of a horizontal line? The slope of a horizontal line is 0, right? So that's how you do a constant. Any derivative of any constant is 0. It doesn't matter with respect to whatever. The linear one, of course, it's just this number here. And we use the power rule for our cubic and our squared, which was up here. One more thing is that derivatives, if you take the derivative with respect to x of a function, and that function had, which is what we just did actually earlier on, but we'll do a slightly different one, of, let's say, 4x squared. So take the derivative of that 4x squared, right? It's actually equal to the same thing as 4 times the derivative of I'm sorry. 4 times the derivative of just x squared, right? And we know what that one is. That one's 2x, see? So whenever you have a constant in a derivative problem, you can actually ignore it and simply bring it to the front before you do the derivative, and then just do your derivative work, right? So this would be equal to 4, and then times the result of this. So the derivative of x squared, we know with the power rule, the 2 comes up front, so it's 2x to the first. Okay, we're not going to leave the 1 there, of course, and then final answer is 8x. So derivative with respect to x is 8x. Okay. And this would work for something with crazy, even negative powers, right? So how do we take the derivative with respect to x? Of, let's say, y equals 1 over x squared, okay? All right, so pause the video, try this, and you're going to convert 1 over x squared to be just a negative exponent, and see if you can figure out how it works. Go ahead. Okay, so what happened? You should have first rewritten this as x to the minus 2 power. All right, and then you use the power rule. So you take the power, in this case, minus 2, move it to the front, right? So I get a minus 2. Leave the x there, and drop the power by 1. So how do you drop negative 2 by 1? It's negative 2 minus 1, right? I'll actually write that out. even though you don't really have to. So you drop the power by 1. See, here with the squared, we dropped the power by 1 from, here we go, from 2 to 1. I subtracted 1. So here I'm doing the same thing. I'm taking negative 2 and I'm subtracting 1, right? So it's negative 2 minus 1. And you should have gotten, of course, negative 2 x to the negative 3 power. Okay, now you can leave it like that, but of course, if you want to be a little fancy, we would do this. And that's the derivative. And I probably should put, just for short, is y prime here. Okay, and that's it. We'll do some homework problems during class tomorrow, and see how you did.